Hi, I'm Kevin. Welcome to my cave. In this episode, I'm continuing our exploration of transistor properties. I have a few loose ends to tie up about transistor beta. We've learned how beta limits the current that a saturated switch can put out, and we've looked at the emitter follower quite extensively. It turns out that we can apply everything we've learned pretty directly to the other two circuits we've touched on, the current source and the common emitter amplifier. I'll start with the current source. To review, we make a current source by taking a transistor, putting some sort of reference voltage on the base, and a resistor to a negative supply or ground on the emitter. The result is that we get a more or less constant current out. We looked at multiple ways to get the reference voltage: a string of diode drops, an LED, a Zener diode, or a voltage reference IC that acts as a programmable Zener, or even just a voltage divider. And even without knowing about beta, we were able to figure out a few things about the circuit. We reasoned that base and emitter voltages must be separated by a diode drop. Ohm's law then gives us the current at the emitter. And we assumed that the base draws no current, so the output current is equal to the emitter current. We didn't have enough information to compute all the component values, but now we do. Nothing that we did so far is very far off. The collector current is a hair less than the emitter current, but we can usually ignore that difference. Now that we know about beta, we can do more. We know what the impedance looking into the base of the transistor will be. It's just beta times the emitter resistor. Or equivalently, the current into the base is the current out of the emitter divided by beta. Just like last time, we know what base voltage we need, and what the limit on the resistance has to be, so we can calculate the values of our resistors. What's the output impedance of a current source? Well, in an earlier episode, there's a link somewhere nearby or down in the doobly-doo, we discussed Norton's theorem, which lets us model a non-ideal current source as an ideal current source with a parallel resistor. And that circuit is precisely equivalent to a voltage source with the same series resistor. If we make a change in the load that results in a given voltage and current difference at the output, then the equivalent resistance is the change in voltage divided by the change in current. That's Ohm's law again. We built a current source in an earlier episode and measured how it behaved. We saw that when the transistor saturated, the collector saw just the emitter resistor, which gave us the slope of the red line. But we said that after that, the current was constant. That would make the output resistance infinite. That's not a problem for the Norton circuit, but it's pretty meaningless for the Thevenin one. But for the most part, we don't care. But if that infinite quantity still bothers you, let's zoom the vertical scale of our plot way in on that alleged flat line. We see that the currents and voltages we measured fall on nearly a straight line, corresponding to an output impedance for this current source of about 389 kiloohms. That's near enough to infinite that we can mostly ignore it. This voltage-current relationship for the transistor is known as the early effect. I might do an episode on it if we ever build a circuit that needs to take it into account. The intercept point of the line with the voltage axis is called the early voltage. It's usually negative 100 volts or so for an NPN transistor. PNPs don't regulate current quite as well, and can have early voltages in the positive 25 volt range. Enough about the early effect. I'm off in the weeds here. In fact, you probably think I've been off in the weeds for the entire video. We were supposed to be discussing the common emitter amplifier, and here I've spent the whole time going on about current sources. Well, we've done almost all that we need to analyze the common emitter amplifier, because the amplifier is just a current source driving a resistor. Couple the signal source to the base with a blocking capacitor, and the load to the collector with another one, and that's all there is to the amplifier. We can choose the component values the same way we did for the emitter follower, working back to front. I find it easiest to do circuit calculations in a spreadsheet. I often start with just a blank sheet and set it up for the problem at hand, but I'll give you a starting spreadsheet if you like. It's on the project GitHub, link down in the doobly-doo. It's pretty close to what we ran through with the emitter follower. I start with the power supply voltage, the load impedance, the gain that I want, the lowest operating frequency, the transistor beta, and the figure for the diode drop between base and emitter. Here I'm using a large value of 100 kiloohms for the load impedance because I intend to run the common emitter amp into a follower. That's a usual practice, by the way. If you try to run the spreadsheet for a low impedance load, you'll find that the component values and currents involved get out of hand pretty quickly. As before, the output capacitor forms a high-pass filter with the load. The sheet sets the corner frequency well below the frequency of interest. The collector resistor has to be much less than the load impedance. The sheet chooses 1/10 the value. We calculate the quiescent point as being the midpoint of the range that the collector can swing to. When the transistor saturates, the emitter and collector resistors form a voltage divider, and that's as low as the collector voltage can drop. When the transistor cuts off, the collector voltage goes all the way to the positive rail. The quiescent current is then found with Ohm's law on the collector resistor. We already discussed that the gain of the circuit is the ratio of the collector and emitter resistors, so we know the emitter resistor. The quiescent current flows through the emitter as well, which gives us the quiescent voltage at the emitter. The voltage at the base is a diode drop higher. The resistance looking into the base is beta times the resistance seen by the emitter. We will set the base voltage using a voltage divider. It needs to generate the correct voltage and have a Thevenin resistance much less than the impedance looking into the base. I'll use 1/10 the value. Now the bottom half of the sheet is identical to what we used for the follower. If we use a simple voltage divider, we need an 11 kiloohm resistance to ground, a 100 kiloohm resistor to the positive supply, and a 10 microfarad coupling capacitor. Our amplifier will have an input impedance of about 9 kiloohms. That's a little low for my taste, but as we saw with the follower, we can improve it by bootstrapping. I ran through that calculation and schematic when we discussed biasing the follower. And I've left you a link to the modified schematic in the spreadsheet. What we designed looks pretty good on CircuitJS. 1/10 of a volt goes in, a volt comes out. But I never trust the math or the simulation. I'll inflict some elevator music on you for a time-lapse of me fumbling trying to get component leads into the breadboard. I'll set up my function generator to a sine wave of 0.5 volt peak to peak, because why not? The result looks good on the scope. Trace 2 looks like a 5 volt peak to peak sine wave. I'll switch over to a triangle wave to check the linearity. It looks linear. No clipping or rounding over the peaks. It looks as if this is a working design candidate. That's about all that I have time for this time. So let's review what we covered in this episode. We looked at the transistor current source. We learnt that its output impedance is extremely high, limited only by the early effect. We learned the limit on the output impedance of the voltage source driving it. And we knew already that the output voltage of the current source cannot fall lower than a diode drop below the reference voltage. Then we moved on to the common emitter amplifier. We learnt that the output impedance is determined only by the collector resistor. This impedance often must be unworkably high, so a high-gain amplifier will usually have a follower as the next stage. We already knew that the voltage gain is the ratio of collector and emitter resistors. While I didn't cover it, if you experiment on your own bench, as I encourage you to do, you'll discover that too low an emitter resistor makes the biasing unstable. We learnt that the impedance looking into the base of the transistor is the emitter resistor times the transistor's beta. The input impedance of the amplifier as a whole is typically much lower than that because the bias network eats up most of the input current. We can make that input impedance a little bit better by bootstrapping the divider network, but that still might not be good enough to match a very high impedance source. Next time, we'll look at an alternative to bootstrapping for dealing with high impedance sources, and go on a quest for higher input impedance and more circuit gain. We may get some surprises, so stay tuned for that. Until then, stay safe, stay healthy, stay curious, and take care of one another. Thanks for watching. Bye.